So my talk mainly focuses on uncertainty quantification techniques that being used for deep learning and some of my case studies that we used uncertainty recently. I am a senior data scientist and AI lead at the University of Queensland in Australia. So here I'm going to just highlight that is in loving memory of my mother and also my father. Without their support, I would not be here today. So I just wanted to highlight this point. This is the outline of my today's talk. First, we discuss uncertainty in general. What is the meaning of uncertainty? And later on, I would like to discuss why we need to quantify uncertainties in deep learning and what is the meaning of uncertainty, machine learning, and deep learning particularly. Later on, main types of uncertainty will be discussed and some of the important uncertainty quantification techniques will be discussed. As I mentioned, I'm going to discuss a few case studies in medical application and LLMs that we have used uncertainty quantification techniques. And finally, research gaps, future directions, final note would be the last part of the talk. So what is the uncertainty in general? So, when we have a kind of like a very, very limited knowledge regarding a future outcome or kind of more than one possible outcome, we have a kind of uncertainty. So it cause in some places that partially observable or stochastic. The main reasons is due to ignorance, indolence, or both of those reasons. It happens because of those, when we ignore or indulge kind of predictions regarding the outcome. So why uncertainty quantification is important? But in real life, we need to know where, when, and why AI model predictions cannot be trusted. This is the main point of having uncertainty quantified. Most of people just focus on the performance rather than knowing where the model doesn't know. And more informed decision making, like, when we have a risk and rewards, we need to have a better trade-off between those items. And also, we have active and curriculum learning. This is more about getting more samples from unexplored regions or for edge cases that they are very rare. And the most important part is getting second opinion when we have uncertain predictions. This is kind of very sensitive regarding critical applications, especially to avoid not having any mistakes, for example, in healthcare. So second opinion comes through in that case, and many more other reasons that why we need to quantify uncertainty. Here I'm talking regarding certainty versus uncertainty and how they are linked with trust with and distrust. As you can see by the figures, you can see that there is a borderline between absolute certainty and absolute uncertainty. As you can see that when we have absolute uncertainty, awareness gonna increase, while when we have absolute uncertainty, ignorance can come through. And this kind of borderline can help we have a trust or distrust. So the uncertainty is the line between trust and distrust that can a result by AI can be trusted or not. In most of cases, people, especially in very critical applications like healthcare, they ask questions how we can trust the predictions made by AI. So this is the question that we need to find how the confident model is regarding the prediction, and this will help to increase trust to the predictions. So the other point that it should be highlighted is uncertainty. Like uncertainty is happening everywhere, not just in AI. It could be happen in our daily life. Uh, for example, if you want to buy a car or a house, everything is like there. We should be considered. Uncertainty in machine learning and deep learning plays the same role. So we make observation like other things using different sources and sensors in the reality, like cameras, and then based on those observations we make decisions. When we have the same observation, we should make the same decision. But the point is changing or happening every moment. We cannot expect to be stable, so we have a very dynamic environment. So the world observation sensors and so on are changeable, so the output should not be changed when those are getting changed. But NL, neural networks and deep learning models are black boxes models. So understanding what a machine learning or deep learning model doesn't know is a very important task to be analyzed. So in that case, it is important to know how confident we can be about the decisions made by AI. So here is the main portal on uncertainty quantification. There are, when we talk regarding main types of uncertainty, basically there are two opinions. Some people believe that there are three types of uncertainties, and while I believe that there are be two major, the, uh, two major types of uncertainty. One of them epistemic uncertainty, and the other one aleatoric uncertainty. So epistemic uncertainty, it happens what the model doesn't know, and it's kind of like training the data is not appropriate. Like we have noises, and due to limited data or knowledge that we have, for example, very limited samples for training, it could be um, uh, you know um, epistemic uncertainty happens, and this is kind of like we can reduce it. So epistemic uncertainty is reducible. On the other hand, electric uncertainty is the natural stochastic of the observation and cannot be reduced even when we give more data to the model. So as I mentioned, epistemic uncertainty can be reduced while electric uncertainty cannot be reduced.
Moloud, quick question.
Yes,
Are these
sure.
uncertainties are mutually exclusive?
Yes.
I see. Thank you.
Okay. So, AI safety and trusted AI. When in the in the daily life, when we are using an AI model that doesn't know when it doesn't know. This is the point. Doesn't know when it doesn't know can be catastrophic for safety critical application like self-driving cars, like healthcare. And a trustworthy AI model must be capable of measuring and communicating its confidence in its predictions. This is the first point. And the second point is say, I don't know or I have doubt when analyzing edge or rare cases. So this is kind of a link between trusted AI and safety. Now I'm going to talk regarding some of important uncertainty quantification techniques being proposed in the literature. I'm not going to, you know, to go all of them. At the end, I will give you a reference that you can go over most of the techniques that I have discussed in a review paper that I have published. A general UQ scope, which is kind of like uncertainty. It comes through, different models like Monte Carlo, entropy, Gaussian, and kind of Bayesian techniques, kind of density-based models, energy-based models, stochastic modeling, and so on, and older ones like fuzzy modelings that being used in the literature. Uh, so to get started, we start with Bayesian based techniques, which I am sure that you are quite familiar with Bayesian techniques, and it's kind of considers a joint distribution of parameters like that and observations y given inputs x, and then it obtains a posterior distribution of parameters during the training, and then it demonstrate of the equation probability of the data, which is often intractable. So here, main steps of the approximation that I have shown here is we need to specify the likelihood and the priors, and then we need to choose the approximation method, for example, MCMC or ensemble variational inference, and so on. After that, we need to generate the posterior distribution and finally do inference for new samples, which is such as averaging or sampling. One of the most well-known techniques called Monte Carlo dropout. As you know
Moloud,
that,
quick question.
yes,
To one
sure.
previous slide, that was the typical approach in the community. Is that how people approach to these approximation problem?
Yeah, it's a kind of very general, but could be, case by case could be changed.
I see. I see.
Yeah,
Okay.
yeah,
Thank you.
you're welcome. So Monte-Carlo dropout, as I mentioned, like dropout, as you know, it being introduced to avoid overfitting, and it randomly eliminates some nodes during training. However, MC dropout is using randomness during inference time, or we call it prediction time, to generate an empirical distribution. As Yaringol in his paper approved is a kind of Bayesian, and it's a Bayesian model, and a dropout network is kind of like a Gaussian process approximation. Here a few of models of baseline neural network that I have proposed, but some of them are trying to drop connects between the nodes. Some of them are Gaussian drop connect, which is they are based on distribution of the connections between nodes, and some of them the nodes being excluded, like Bernoulli dropout or Gaussian dropout, which are the nodes are based on the distribution. And the other type is spike and slap dropout, which is they are also exclude some nodes, and the connection between the nodes are distribution based. The other well-known method called variational inference, or VI for short, VI actually aims to estimate the posterior distribution by a learned variational distribution of weights with learnable parameters. So this approximation actually is enforced by minimizing the KL divergence between those prior and between PW by data and the priors. And this is done through maximizing the evidence, which is we call it elbow. Here I showed in the equation. For more details, in this figure, I have shown different variational inference that being proposed in the literature by different case studies and in different situation, which like tied parameters or free parameters that they have decided to contribute in terms of working on the case that they can improve. So the larger region in this figure, which is the orange color, shows the space of all possible distributions. This is all the possible. The orange point represent the posterior. This is the posterior that we have. The inner region, the blue one, despite the space possible variational distributions. The optimized variational distribution, which is a blue point here, the blue point, has the smallest distance to the posterior distribution, which is here. And as you can see, this is the point that we use variational
Question,
inference to
Malud.
make this. Yeah, sorry, sure.
What's the metric you use for distance calculation? Is it KL?
Uh, yeah, yes, exactly.
Okay.
Yeah, so some people recently used the occlusion distance and so on. So kind of like normal distance metrics as well. And the other well-known method, I think, Shoaib, you are familiar with deep ensemble. Most of us, we have used ensembles, but deep
Mhm.
ensembles, we train an ensemble of M networks, different networks with different random initialization. And then we have, a kind of like mean and variance or standard deviation of the predictions of those M networks. So the assumption is network will behave similarly in areas of sufficient training data, and prediction will be completely different where there is no data available. So it's a kind of epistemic uncertainty here. So deep ensembles can capture both epistemic and electric uncertainty in their nature. We have something called Monte Carlo dropout ensembles, which is a very easy model, to be honest. Is kind of like they have during inference time. If you remember, we were talking about MC dropout. They have kind of network that they kind of randomly uh, exclude some of the nodes of the each network. For example, here is 0.3, so 30% of the nodes, for example, this is at random, show. So for example, zero point 0.3 of the nodes gonna be excluded. So this is during inference time, and then by calculating mu, which is the mean, and here like a the variance we will do. Variance shows the uncertainty level, and mu would be the final prediction of the models, the M networks that we have. Now I'm going to talk about application of UQ techniques that we used for medical cases studies. At the end, I just give one example for large language model as well, which recently being published, accepted, not published yet, but just accepted a few days ago by TMLR. And the motivation behind of research for medical cases is uncertainty in many real medical tasks happening, like medical image classification, segmentation, signal processing, and computer-aided decision support system for very critical medical applications. One note about UQ is that alone cannot solve issues. So we should not expect that having one uncertainty quantification can solve everything. And we planning to develop system based on the uncertainty. We should have the uncertainty integrated into the final model. So somehow is kind of um, an addition to a model which can be more reliable for the predictions. Here I will give you one example. Let's say we have a very simple binary classification of um, uh, images for skin cancer, for example, malignant and benign, that we have two binary. A kind of like the training environment, because the model has seen those samples previously, it can be, do prediction very well. However, how about during testing time, we gave a rare image that never been seen during training. In that case, the model can be very, very, uncertain regarding a prediction. So is the model reliable for medical diagnosis? This is the question that we need to answer by including uncertainty quantification. So one of our case study was skin cancer classification. For these, we had very well-known data set for skin cancer, which included like 2,637 images, and we had another data set that was I exactly don't remember the numbers, and we used different deep learning methods like CNNs and so on. And then we proposed a novel idea called three-way decisions based on the entropy for this skin cancer classification. This is the general view of the proposed model, which is we have a three-way decision based on the models. So in the first stage, we have a deep ensemble including different of them, and then we have defined a threshold, which is we called certainty threshold. And if the entropy is smaller than those, it's gonna go to the prediction directly. While if it is not, it goes to the second stage. So we do as like multi-stage predictions. And when we did that, we had a one stage here that we have added to the model, saying that for rare cases we did not do predictions because we didn't know. We returned those samples saying that we don't know or we are uncertain. So this is exactly with the nature of uncertainty quantification. We should not, do predictions while we are not certain. So in this model, we try to make this happens by designing a model that doesn't include samples for the predictions while the model is not confident.
Moloud, question one,
Sure,
please.
sure, sure.
Just curious. So it's a two-level decision-making mechanism, and
Exactly.
so the deep ensemble model is identifying the uncertainty region, and then you
Yes,
use a drop model to even go maybe finer uh, regions of uncertainty, and
exactly.
therefore you've got a maybe a smaller region of uncertainty, and you're still making relevant decisions between benign and malignant. And I'm curious, could you please provide us some insights about how the dropout model is useful to make such finer and better decisions in those uncertainty regions that are characterized by the one previous ensemble model?
Yeah.
What's the
Mhm.
insight behind it? Why would I expect, for example, the dropout model to help me in that particular case?
Yeah, so it's a good question. To be honest, we try to be more tough to the model's prediction. So every time why we did, the reason is we wanted to see model when it challenges with the very kind of like that confidence certainty threshold, we made it smaller and smaller. So we forced the model to be very, very, how can I say, confident regarding its prediction. Otherwise, we would not expect. So that's why the
Hmm,
second stage is the tougher to go through all the details left from the first stage.
I see. I see.
So,
I see.
so we try to deeper understand exactly what's happening exactly in uncertain regions. Finding
Uh,
uncertainty is okay, but why exactly and where because it's the uncertainty has density. In some places has more, and in some places has
correct.
less, right?
Correct. Correct. Yes.
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 Yeah.
So the
So that's why we
regularization in
use
that
uncertainty.
case, so regularization in that case is helpful to
Exactly.
identify where these denseness is distributed in that
Exactly.
uncertainty landscape. I see.
Exactly. Yeah.
Okay. Okay. Thank you.
Thank you. So here we had two phases of answers, evaluation, and you can see that even though in the second phase that kind of like we had a little bit like let's say accuracy improved and a little bit AUC less than the first stage and F score less. But the point is we have more confident in the second phase. This is what we are exactly looking for. Even killing a little bit of accuracy or F score, but with higher confidence will be more acceptable according to the clinicians that we ask them. So, for example, here we I have provided two predictions. For example, for high uncertainty and low uncertainty. Here you can see that the overlap between distributions, they don't have overlap between two classes. This shows that model is very confident regarding its predictions. However, if you look at these two images, the right sides, these two, two classes, they have overlap. It shows that the model has kind of like it's very uncertain regarding prediction. Here is uncertainty is very high because the distribution of two classes are very close to each other. And this is the way that we help predictions and make decisions. In another case study, we did the same for
So,
medical
Maluk,
image classification. Yes, please.
do I understand it correctly? So you're saying that there is a natural trade-off between accuracy and elimination of uncertainty. Is that the true statement?
To be honest, not in all the case. In
Not
our
in all
first
cases.
yeah, not always. For example, here we because we had two stages. We were happy to have less accuracy but more confidence.
I see.
And I just
Okay.
wanted to be very tough regarding the predictions. In other like in our next papers, I will show you that even we had the uncertainty quantified, we could improve the performance as well. The accuracy has been improved.
And are you also exploring the conditions under which, such trade-off, for example, would exist or would not exist? For example, making it less uncertain could be helpful to boost the accuracy, for example, but in what under which conditions, for example, that's true, could be a
Yes,
nice contribution to the literature because in different fields, particularly in health and maybe in automation, etc., people, if they know the conditions, they will push for reducing the uncertainty and they will know that there will be payback, which is improved accuracy. But under other conditions, maybe they have to pay the price, that they give
exactly,
away the accuracy and in return they get the better uncertainty elimination. So
exactly.
those conditions might be, I don't know if they're if we identifiable, but I'm just curious that if these conditions can be set out like in exact mathematical terms, for example.
Yeah, to be honest, myself, I haven't done yet, to be honest, on this point, but we try we are trying now one of my PhD students is like we are trying to prove theoretically how it works in terms of whether there is any condition that performance gonna in any condition that decreases the performance or it can help to improve the performance as well, but we haven't we have not found anything very meaningful yet, and we are still exploring, to be honest.
Thank you, Mel.
Thank you. So in another case study, we did image classification, but for kind of not binary classification. We did it for multiple classes and for different types of images, like very challenging one, like OCT, which is very noisy images. We had I think it was early 2020 when COVID-19 was a very hot topic. At that moment, we got some COVID-19 data from the CT and kind of X-rays and skin cancer again. We proposed a model called binary residual feature fusion. I called it BAV. And the proposed model has two main strategies, direct and cross connections, and validated on four data sets. As I mentioned, one of them was like a RGB image, the skin cancer, and three grayscale images. We also use the Monte Carlo dropout used to quantify uncertainty. So here, as I mentioned, that we have both direct and cross of the connections. And here we used an idea, as you know, that we have a traditional binary tree, which we come from um, top to the bottom, but we did a reverse binary tree, which is we did a kind of combination, which we used exact way of reverse binary tree, and both direct and cross based BARF models use the binary tree combination strategy. This is the other distributions for skin cancer, for example, that we have shown. As you can see that kind of like correctly classified or misclassified, this is like two distributions and they are far from each other. It shows that the model is very, very confident. And the same thing for the other sample, that sample B. And again, these distributions are far from each other. It shows the model is confident for predictions, and we can somehow trust the decision made by the model. At the end, we have compared the obtained results with some of the uh, state-of-the-art models in the literature. As you can see that, for example, for OCT, our model could almost be uh, one of the best in terms of performance and almost beat all of the previous methods. For skin cancer, almost the same thing in the X-ray and OCT and COVID-19. But for COVID-19, to be honest, some of the studies they haven't provided the code, so we just try to, based on the recommendation from reviewers, include them. Even though I was not happy because they had different data sets and also kind of like baselines they use like ResNet or AlexNet and so on. In another case study, we proposed a model which was Hercules, which we used a kind of a combination of hierarchical attention fusion block with multi-level feature fusion block, and then we concatenate them and then give it to classification for final prediction. This work was published by IEEE Transaction on Industrial Informatics. We validated the performance of the proposed model on three different medical image dataset and consider uncertainty in the attention mechanism, and then we proposed a multi-level fusion modules. This is the general, the detailed overview of the proposed Hercules model. As you can see that the proposed Hercules model includes two main fusion blocks. CA, which is a normal, is a cross attention, is the channel attention module with normal dropout. And then we have channel attention with uncertainty, which comes with Monte Carlo dropout as our uncertainty quantification modules. And finally, SA, which is a special attention being added into the model in all the layers. This is the details of the channel attention, normal one, and with dropout and Monte Carlo dropout, and our used channel attention. As you can see, we compared the performance like other studies with the state-of-the-art models and some of the existing ones, as the reviewers also again asked us to compare with some studies. For example, you see for OCT, some studies had much less image input. You see that samples are very small, but we still compare, and we highlighted the performance. As you can see, um, we could beat them in terms of like precision, recall, F score, and accuracy. And one point that I wanted to highlight, there are very few studies that they are considering uncertainty quantification. For example, for OCT, only three studies, and you can see that in, for example, X-ray, just two studies they have used. Now I'm going to give you another one that we used in real data set. This is a CSX classification, which we have collaborated with the Tehran University of Medical Science in Iran. So the data is the real data, and CSX is very rare heart disease that is because it's a heterogeneous entity, both clinically and pathologically, involving various pathogenic mechanisms. So based on that, we try to collect our own data sets and use it for the based on the classification. So here we propose a model called mixture of Bayesian experts. So it's a kind of different with it's somehow different with MOE, mixture of experts. We try to involve Bayesian in terms of predictions. This work actually published by Information Fusion. So for these data sets, we had almost 90,000, over 90,000 patients, and then no positives and no typical chest pain, excluded. And final study population was 2,530 patients, which 1,990 had a CAD, and the other one like around 540 with CSX. This data was collected from September 2016 to June 2018 in Tehran. Here I'm showing you a few simple and well-known mixture of experts. As you know that in a simple one, which is shown in the left side, we have several experts and one gate to give away to each prediction made by each expert, and then weighted sum will be calculated and final prediction will be made. However, there is another model that they have multiple, a kind of cluster of experts and a kind of cluster of gates to control each of these weights. This is a kind of a better MOE in terms of prediction, but it's a computationally expensive. There are two more, which one of them is called hierarchical mixture of experts, HMOE, and another one is multi-treatment efficient estimation. They call it M3E2. These two mixture of experts are a kind of multi-stage predictions. And as you can see, for example, here they have gates in not just one level, in two levels, which is makes it a better prediction. And here they have a kind of like you see they have from the experts, they get the same inputs, but the gates are not getting the same inputs, which makes it more the prediction more at the end the final prediction will be much stronger. However, what we try to do is kind of try to involve humans and make sure that the machines and humans do kind of like selecting the features, because our data set included a lot of features. When we talked to the clinicians, they said they make decision based on very important features. So to do so, we asked three clinicians to select their own features, and we did three feature selections, like machine learning based feature selections, and give it to kind of like two experts. As you can see, we have the same as multi stage gating to give the prediction. So here like odd and even express are calculated. You see E1, E3, E5, 7, 9, and 11 here in the orange, and you see E2, 4, 6, 8, 10, and 12 here in the green ones. We try to separate them and combine them, the beliefs from different experts, and a kind of human machine integration predictions. After developing the model, we try to compare. To be honest, we try to consider CSX. The point was most of studies they did not consider CSX. They just normally work on cardiovascular disease, and we try to make it more difficult. And as you can see, most of case studies
Malut,
on.
we have a
Yes,
question
please.
from the audience. Omar is
Sure.
asking, is the mixture of expert architecture, is it inherently robust to uncertainty?
This one.
Yeah, mixture of experts in general, for
Yes.
example, is it
In
inherently
general.
provides such robustness to the uncertainty?
Yeah, exactly. It does. The reason is we can look at the mixture of experts as an ensemble model, right? So technically, ensemble methods are very well known uncertainty quantification techniques, and MOE is a part of it.
I see.
So
Thank
they
you.
are robust. Yeah, you're welcome.
Thank you.
Um, One good point about this is, to be honest, we try to ask like we ask clinicians to do predictions, and our model even could do almost but better than humans in terms of prediction with higher confidence. So what I was planning to do that give 100 samples to the clinicians and ask them to the predictions, and then ask the same thing with the developed model, and we could see that our model can do very good predictions, very close to humans, and this is a good start that the model is confident in terms of predictions. And now we try to move to medical image segmentation, and for this one we proposed a new model called attention guided hierarchical fusion unit. Here I have shown a different unit architecture like unit plus plus, unit 3 plus, and our model, which is a hierarchical attention guided. The point is this model is uncertainty of a version of the old one, which called UAE-AF unit. The general view of the proposed model is here. You can see that we have different modules in skipping connection between encoder and decoder. And also when we have the uh, decoder, we have a module called DAF3, which I have shown here. I think yes, here. So each of them like DAF1 and DAF1, which is UAF normal one, being used to scale the images and try to capture uncertainty when we do a downsampling. Sorry, to we do a kind of like a transferring feature from each layer and transferring to the encoder side. This is the map which shows the predictions made by three models, which is the uh, our model is very long to be honest, but unit plus plus and unit, and you see the region which shows that kind of like with red is the uncertain region, which shows that how these models are confident regarding the prediction if we have kind of like very close to each other. So our methods performance was very close to unit plus plus, but the point is our model also captures its uncertainty. So this is the point. Even we get the same performance as other state-of-the-art methods, we we believe that having with higher confidence will be more important and it will be more reliable. Here we have, fairly compare with the existing methods. And as you can see that in most of cases, our model is, in terms of accuracy, dice, and IOU, and specificity is among the best. However, in terms of sensitivity for ISIC 2017 was not among those. We have tested on three different data sets, which ISIC 2016 was involved as well. Uh, So now I'm getting back to another study which we involved Bayesian approach to test time augmentation. Test time augmentation is very well known technique to do uncertainty, and it does it. Test time augmentation is somehow very close to like do ensembling of the model's prediction. Here, we used a Bayesian model averaging rather than simple, mm, simple averaging that mostly TTA models are doing. We tried to use these BMA involved for the predictions and to see how they work. So we evaluated on different data sets, including three medical image data sets like skin cancer, breast cancer, and chest X-ray images, and two well-known gene editing data sets. So the gene editing data sets would then we transfer to the image-wise. This work was published, if I'm not wrong, yes, knowledge-based system. Here is some of the results. As you can see that we have used the models for these three data sets, that image data sets. You can see that our results, which involved in different version, it they can like definitely beat other models. In just one case for chest X-ray, um, uh, we have uh, we have the same performance as the reference 14 in our case study. However, you can see that by number of samples, how we kind of application study, when we increase number of samples and the correlation between accuracy and number of samples, we definitely can work better than TTA. So if you remember, I told you that we will show that there is no connection between, in some cases we still deal with uncertainty, but still can work better than
Yes, I do
other
remember.
mode. Exactly. So you see that, for example, we use the different backbones like DenseNet, ResNet, and VGG. You can see that we can definitely improve the accuracy compared to the sample size
Yeah,
that significantly compared to normal TTA. Bay
right.
TTA works way better.
I see.
And here is kind of like we have tried to include kind of like because we used kind of let's say when we talk about TTA we need to have augmentation, right? We need to do different augmentations, and we here try to involve like rotating, zooming, and shifting as a base augmentations, and like merge them together. You can see that BTTA in terms of standard deviation, which is the kind of like the metric of measuring uncertainty, is almost has less STD compared to other methods. However, the accuracy is much higher than other methods like TTA, VGG, MobileNet, and so on. And now I'm just give you a very quick one, which we used the
Malut,
uncertainty for.
we're almost
Sure.
end of the we're running a little bit of out of time, and so
Yeah,
if you could just
sure.
wrap it up, that would be great for the audience.
Sure, sure. So you want me to jump quickly? Just a quick one. Here we try to uncertainty be involved with conformal predictions for mixture of prompts in networks. And here we did it for language only architecture and for multimodal, which we included clips. And the results, as you can see, we improved a lot in terms of performance, like nearly 1%. And the paper got published by TMLR. And this is some advantages and disadvantages of the UQ methods that you can find it in my review paper, a review of being published by Uncertainty by Information Fusion. And this is some of our collaborators that we have collaborated in the past few years. Thank you so much.